Problem is obtain half-range Fourier cosine series to the function x sine x in the interval 0, pi. Hence show that this deduction. So first we find half-range Fourier cosine series. Half-range Fourier cosine series to the function f of x means f of x equal to a0 by 2 plus sigma n equal to 1 to infinity an cos nx. This is half range Fourier cosine series. Here to find a0, formula given by a0 equal to 2 by pi integral 0 to pi f of x dx equal to 2 by pi integral 0 to pi f of x is x into sine x dx. Here now we have to do the integral evaluation. Here under the integral x algebraic and this is trigonometric. Clearly algebraic into trigonometric. So we go for generalized rule of by parts by taking algebraic as u and the trigonometric function as v. For u derivatives u double dash 0. For v integrations v1 equal to minus cos x, v2 equal to, for cos integration is sine, so minus sine x. So by keeping formula in mind, 2 by pi u v1 x into v1 is minus cos x minus u dash v2 that is minus sine x. Limits 0 to pi. So 2 by pi, by substituting upper limit minus pi, we know cos n pi equal to minus 1 whole power n. So cos pi means in place of n 1, that is minus 1. Cos pi minus 1. Sin n pi equal to 0. For n equal to 1, 2, 3 and so on, sin n pi 0. That means sin pi 0. Upper limit substitution minus of lower limit substitution 0 into this term 0 and sin 0 0. So you got 2 by pi minus 1 that is pi. You will get 2. Therefore a0 equal to 2. Now to find an. To find an, formula equal to 2 by pi integral 0 to pi f of x cos nx dx equal to 2 by pi integral 0 to pi f of x is x into sin x cos nx dx equal to 2 by pi integral 0 to pi x into, under the integral x into two trigonometric functions present in product. First convert these two in terms of their summation so that easy to apply integration by parts formula. So take this as a sin A cos B together with these two. 2 sin A cos B means sin of a plus b plus sin of a minus b. Already we used this 2 in this formula. That's why you will get 1 here. 2 sin a cos b equal to sin of a plus b plus sin of a minus b. Now 1 by pi integral 0 to pi x into, for our convenience just write down this as n plus 1 of x and here minus of sin n minus 1 of x. If you take minus sin of minus theta, that becomes minus sin theta. And take x common here and here, that makes further simplification convenient. Next step is equal to 1 by pi integral 0 to pi x into sine of n plus 1 of x dx minus 1 by pi integral 0 to pi x into sine of n minus 1 of x dx. Here we split the single integral into two integrals. Take this as u and this as v. U dash equal to 1, u double dash equal to 0, v1 equal to, for v integration is, for sine integration is minus cos of n plus 1 of x by n plus 1, v2 equal to, for cos integration is sine minus sine of n plus 1 of x by n plus 1 whole square. By the generalized rule of by parts, uv1 x into minus cos n plus 1 of x by n plus 1 uv1 minus u dash v2, so sine n plus 1 of x by n plus 1 whole square, uv1 minus u dash v2 minus 1 by pi. Again here also this is u and v, this is uv1, u is x, v1 is minus cos n minus 1 of x by n minus 1, uv1 minus u dash v2, v2 means sine of n minus 1 of x by n minus 1 whole square. Limits are from 0 to pi, here also limits 0 to pi. Now equal to, by substituting upper limit pi, you will get minus pi minus 1 whole power n plus 1 by n plus 1. Sin n pi 0, so this term 0, sin n pi 0 and sin of n plus 1 of pi, that is also 0. Minus of lower limit 0 into this term 0 and sin 0 0, so you will get only this term minus 1 by pi. Here also minus pi into cos of this term minus 1 whole power n minus 1 by n minus 1, and for this term 0 by substituting in place of x pi, and lower limit 0, 0 into this term 0, sin 0 0. So pi cancel, here also pi cancel. Minus 1 whole power minus one more minus sign, that means n plus 2 by n plus 1, minus minus plus, so plus minus 1 whole power n minus 1 by n minus 1, it is equal to, this can be written as minus 1 whole power n into minus 1 whole square by n plus 1, and this can be written as minus of minus 1 whole power n by n minus 1. At a minus 1, here we got that minus sign. This is 1 fixed, so by taking minus 1 whole power n common, 1 by n plus 1 minus 1 by n minus 1. Undoing the simplification by taking LCM, a plus b, a minus b, a square minus b square. Here you will get n minus 1 minus n minus 1, cancel. So minus 1 whole power n into minus 2 by n square minus 1 can be written as 2 by n square minus 1 into, include here minus sign, minus 1 whole power n plus 1. Therefore, here we are finding half-range Fourier cosine series. Already a0 determined and we got an. Therefore, f of x equal to half-range Fourier cosine series. cosine series f of x equal to a naught by 2 plus sigma n equal to 1 to infinity an, that is 2 by n square minus 1 whole power n plus 1 into cos nx. This is half range Fourier cosine series to the function x sin x. Here f of x is x sin x, and after finding this they ask to show that, and we need to obtain this deduction. In order to obtain this deduction, first expand this sigma. So x sin x equal to 1 plus, and if you try to expand this sigma, here you have 2 common, okay, 2 into, for n equal to 1, for n equal to, here once observe in the denominator we got n minus 1. That means in particular this is for n not equal to 1. This is an value for n not equal to 1. We have to determine for n equal to 1 also. So if you determine for n equal to 1, you will get a1 equal to minus 1 by 2. You will get a1 equal to minus 1 by 2. So you will get minus 1 by 2 also here. So minus 1 by 2 cos x. This is half range Fourier cosine series, and in order to obtain this deduction, expand this sigma, that is 1 plus minus 1 by 2 cos x, and in particular for n equal to 1 over, and this is from n equal to 2 onwards. So if you put n equal to 2, (1 by 3) n2, you will get